Welcome guys to the another video of image-based lighting in PBR. Before moving forward to this video, you should watch BRDF video to get a grasp of this video better. So let me first introduce the Lambert rendering equation. The Lambert rendering equation defines the outgoing radiance in terms of the emitted radiance and the reflected radiance. First, the emitted radiance is always equals to 0 if the surface is not emitting. And the reflected radiance, this integral part, is calculated over the hemisphere. So it contains two parts. First is the BRDF part and the second is the irradiance part. BRDF defines the reflectance properties of a surface, and the second part, irradiance, is calculated by the incident radiance Li multiplied by the dot product of omega I and surface normal n. Calculating the integral in extended Lambert rendering equation can be computationally intensive, especially in the complex scenes. This is where Monte Carlo integration comes to the rescue. Monte Carlo integration is a powerful technique that uses random sampling to approximate the integral. By randomly sampling directions on the hemisphere, we can get a good estimate of the integral's value without having to evaluate every direction. Let's try to solve the equation further. As we have seen previously, the BRDF term can be further divided into the diffuse component and the specular component. So when we put this in the rendering equation, we can achieve the diffuse term and the specular term. We will try to solve both of these terms in the code separately. Take a look at this 3D environment. It's featuring a cube map and a series of glass jars. This is the diffuse part that we are gonna solve right now. Now let's dive into the GLSL compute shader code for computing diffuse irradiance. Let's just start by defining the version or GLSL. And then let's just define some variables that we are gonna use. So the first one is pi. We are gonna use epsilon to compare floats. Also, we are gonna use a variable for 2pi. Next, define the number of samples with For a good balance, we are gonna choose number of samples is 64,000 64 into 1024. Then we are going to define variable for inverse sample. Then input cube map for convolution. Binding should be 0. Let's name it input textures. Then we will define a write-only output cube map to store the computed irradiance value. Just name it output dash. Okay. Now let's jump onto the main function. My bad. Let's define a function called getSamplingVector. This function calculates a normalized sampling direction vector based on the current fragment coordinates. You can think of it as determining where we are currently looking in the cube map, given the execution ID of our fragment shader instance. The function begins by calculating vector st that holds the normalized coordinates of the current fragment. These coordinates are scaled by the size of the image we are writing to, which gives us normalized texture coordinates between 0 and 1. Next, it remaps these normalized coordinates to the range -1 to 1. In the context of a cube map, this corresponds to directions covering a complete sphere around a point. Depending on the face of the cube map we are looking at, denoted by a z component of global invocation ID, we calculate our output vector differently. Essentially, this step is responsible for projecting our 2D texture coordinates to 3D direction vectors. After that, the function returns normalized direction vector. Next on our list is the compute basis vector function. This function helps us in calculating an orthonormal basis for the tangent space of point on hemisphere we are currently sampling. The function takes as input a normal vector and calculates two other vectors, the tangent and the bitangent, which are perpendicular to the normal vector and to each other. This creates an orthogonal coordinate system or basis. The choice of tangent and bitangent vectors isn't unique. There can be many sets of tangent and bitangent vectors that form a valid basis with normal. In this shader, we chose a bitangent that is orthogonal to the normal and up direction. If normal is too close to the up direction, we fall back using 1 0 0 direction instead. After choosing the bitangent, we calculate the tangent as the cross product of normal and bitangent. Both bitangent and tangent are then normalized to ensure that they have unit length. The compute basis vectors function plays a critical role in transforming the direction vector sampled in the tangent space of the hemisphere to world space directions that can be used for fetching texels from CubeMap. Now let's move on to the next part. We will define a vec3 irradiance variable. This variable is initialized with the value of 0. It is used to accumulate the incident light that reaches that point over the hemisphere. In the context of our shader, it represents the diffusely reflected light from the environment. Next, we have a for loop that runs a fixed number of iterations defined by number of samples. Within each iteration, it takes a sample from Hammersley point set, converting that to a direction in world space and using it to sample the cube map. The color from the cube map is then accumulated into our irradiance variable. The reason for using a loop is to perform Monte Carlo integration. This process uses random sampling to compute an approximation of an integral, in our case the total light incident on a point from all direction in the hemisphere. The term Hammersley refers to the Hammersley point set, a type of low discrepancy sequence used in stratified sampling. When used in Monte Carlo integration, this type of sampling reduces variance and helps us to converge the correct result faster compared to purely random sampling. VDC function inside sample Hammersley is an implementation of Vander Corput sequence in base 2, also known as bit reversal. This function generates a radical inverse of a given 32-bit unsigned integer. It takes a 32-bit unsigned integer as an argument, performs a series of bitwise operations to reverse the bitwise in the integer, and returns the reverse integer as a float in range of 0 to 1. This helps in creating a sequence of numbers that are more evenly distributed than a purely random sequence. This is especially important in Monte Carlo methods where we want to minimize the variance of the result. The next crucial function in our GLSL compute shader is sample hemisphere. This function is responsible for converting the two-dimensional Hammersley point into the three-dimensional points on the hemisphere, which is essential for our Monte Carlo integration process. U1 and U2. These parameters are components of 2D vector that we previously obtained from 2D Hammersley sequence. Here's what happened inside this function. The U1 value is used to compute the height of the point on the hemisphere along the z-axis. It takes map into range of 0 to 1, ensuring it stays within the hemisphere boundaries. This is done by invoking the max function. Now, what about U2? It is used to calculate the azimuthal angle around the hemisphere, determining the x and the y coordinates of the sampled point. How do we do this? We apply the cos and sine functions to 2 pi multiplied by u2, which effectively transformed u2 into a circular value around the hemisphere. The outcome of this operation is multiplied by projection of u1 on the hemisphere plane, named u1p. So what does this function return? It's a three-dimensional vector representing a uniformly distributed point on the hemisphere. This is particularly important as it enables more accurate sampling, contributed to achieving realistic indirect lighting effects. Now we have generated a uniformly distributed point on a hemisphere, given two random numbers. However, the result is still in tangent space of the surface and doesn't correspond to any real direction in our 3D world yet. For this, we use the tangent to world function. The tangent to world function is used to transform vectors from tangent space to world space. It takes in a vector v in the tangent space along with the normal, tangent and bitangent vectors that form an orthonormal basis in world space. Once the x component of v is multiplied by the tangent vector, the y component of v is multiplied by the bitangent vector, and the z component of v is multiplied by the normal vector. The sum of these products give us the equivalent vector in the world space. This function is essential as it allows us to transform the direction of light that we calculated in the previous step from being relative to the surface of the object to being absolute, world-based directions. We can use this information to sample the environment map and determine how the light from those directions would affect the color of the surface. After we have sampled a point on the hemisphere using Hammersley point set and transformed it into world space, we need to calculate the contribution of that sample to overall diffuse irradiance. Let's calculate the cosine of angle between sample vector and the normal vector. The dot function calculates this for us. The max function is used here to ensure that cos theta does not go below 0 and can lead to unrealistic rendering artifact. We then add this contribution to our accumulated irradiance. For each sample, we calculate the irradiance coming from that direction by fetching the corresponding texture from CubeMap using text load. This radiance is then weighted by the cosine of angle between normal and sample direction, which models the Lambertian reflectance. The reflectance is also multiplied by 2 due to integration over the hemisphere. Finally, the weighted radiance is accumulated in irradiance variable over all the samples, which after the loop ends gives us the average irradiance incident on the point over the hemisphere. Lastly, we will store our irradiance in the output texture. Let's turn our attention to the scene we have worked on so far. We have now successfully calculated the diffuse irradiance part of the integral. As you may observe, our objects appear rather dim, a direct consequence of the fact that the specular reflections are missing. The link to this project is in the description. In our next video, we will delve into the fascinating world of specular lighting, so stay tuned. If you found this content interesting or you have some insights to share, I encourage you to reach out and connect with me.